All right, now we know how to evaluate integrals. We can go back, let's revisit finding area. And in particular now, let's find the area between two curves. So here we're gonna find the area between y equals x squared minus 2x and y equals 3x. Step number one, I would suggest strongly, is sketching a graph. This you should recognize as a parabola. That is a line through the origin. So the graph would look like this. This parabola, if you factor out an x, you can always make that x. This is x times x minus 2. And if you set that equal to 0, you can tell that this parabola would have x-intercepts at 0 and 2. Okay, this number is 2. Y equals 3x is a line, actually with a pretty steep slope, but so I could fit it on my graph, I made it not so steep. So there'd definitely be some area between those curves. You want to find the intersection points in some cases. Just by drawing it, we can tell that they intersect at 0. And if I set the two y values equal to each other, if I set the equations equal to each other, I can determine the other point of intersection is when x is 5, which gives me 15 by plugging it into either one of those for the y value. Okay, so finding the area between two curves, it is the same idea where we're imagining rectangles. Previously, though, we just had our rectangles going from the, here to the x-axis, but we're going to fill this whole region up with a bunch of thin vertical rectangles, just like we would do if we were doing a Riemann sum. Okay, and they're infinitely thin. And as we know, the way to think of an integral now, it's an adding machine, right? The fundamental theorem of calculus gave us a way, if you can find a formula for the area of every single one of those rectangles, the integral will do the job of adding up the areas of an infinite number of rectangles to give us the total area. One reason I selected this problem is that part of our area goes below the x-axis, and we've talked about how, generally speaking, when you integrate a function, if you're below the x-axis, it comes out to be negative, right? And so part of my area is positive, part of it's negative. But if we do this correctly, we won't have to worry about, even if the graph is below the x-axis, we will get the correct area. As long as we find a correct formula for the area of any one of those rectangles. So how do we do that? Well, the area of a rectangle is height times width. And the height of any one of these rectangles that we put inside in this region here is always going to be the top function minus the bottom function. For instance, let's say I consider the rectangle right at x equals 1. If I want to know how tall it is, I could plug 1 into 3x, and that would tell me the rectangle stretches up to 3 on the y-axis. If I want to know how low it goes, I can plug 1 into my parabola, and that gives me -1. So what is this height? Well, most people can quickly tell me it's 4, but how do you get 4 with those two numbers? If you subtract 3 minus -1, that gives you the correct height of 4, right? So it doesn't matter if you have a negative value here. As long as you do the top minus the bottom, you will get the correct height of any of those rectangles. In general, at any random x value, what's the top of my rectangle? It's going to be whatever 3x is, right? At some x value, it's going to be 3x. What is the bottom? That would be the parabola, x squared minus 2x. The thickness, okay, we talked about the delta x is dx is kind of like your infinitely thin delta x. That represents the widths of those rectangles. It's an infinitely thin increment of x. Then you would just integrate, add up all of those rectangles from 0 to 5 of this formula. And of course, to work it out, I'd probably distribute the negative and simplify, combine a couple terms. And this will give you 5x minus x squared. Using your fundamental theorem of calculus, find our antiderivative. x squared over 2. That'll be 5 halves x squared. This one goes up by 1, minus x cubed over 3. Plug in the 5 to both of those, minus what you get when you plug in the 0, which is nothing, right? If you plug in the 0, you get nothing. I should put minus 0, right? And I got an answer of 125/6. Let's look at another example. Okay, for this one, we're going to set up, we're not going to actually work this one out, the integral or integrals for the area between y equals x squared, y equals 1 over x, and y equals 9 in the first quadrant. And I said step number 1 is to sketch it. I've already provided the sketch, but just to walk you through it. 1 over x, you may recall, that's the graph that, it's actually a hyperbola. It has 2 parts. The other part's in the third quadrant, but we're only in the first quadrant. Looks like this. Here's y equals x squared. Here's y equals 9. So this little triangular looking region is what we want the area of. Now, one thing, we talked about filling up the region with rectangles, and one thing you'll notice, the height of our rectangles, we like to go top minus bottom, right? We learned from the previous example. But what do we notice is that my bottom function changes depending on where we are on the graph in the region. Because of that, what we need to do is break this up into 2 integrals. Okay, we're going to do one integral. Okay, I found these points of intersection by setting these equations equal to each other. So this point right here, the x value is 1/9. And so I went from 1/9 to 1, which is where the parabola and 1 over x intersect. The top function is y equals 9. The bottom function is 1 over x. So I can integrate from 1/9 to 1. That'll give me the left half of this region. And then I can go from 1 to 3 on the right half. Top function is still 9. And my rectangles hit y equals x squared on the bottom. And so I would have to work out both of these integrals and add them together to get the total area. Now, there is, if you had to actually work this out, you'd have to do 2 integrals. So there'd be a bit of work to do here, right? Wouldn't it be nice if I could just do this integral with only, find this area with only 1 integral? And there is a way. Okay, we have to think a little bit differently though here, right? We know an integral is an adding machine. We've been using it to add together the areas of a bunch of rectangles. And we have so far just lined up our rectangles vertically. Makes sense. But there's no reason the rectangles have to be lined up vertically. So what we're going to do now is do the same area using horizontal rectangles. Because if you fill this region up with a bunch of horizontal rectangles, to find the area of any one of these rectangles, instead of top minus bottom, we're going to go right minus left. That would give us the total length, if you will, of one of those rectangles. Right minus left. And notice every rectangle I put in here always hits the parabola on the right, and it hits the 1 over x function on the left. And my top rectangle would line up perfectly along y equals 9. It's a horizontal line. Okay, now a big thing we're going to have to recognize though is that if we're going right minus left to represent the length, what about the thickness? What about the width? The width of one of these rectangles now is not a dx. That would be a small increment of x. If I take this back to the y-axis, this width is a small increment of y, which we would denote as dy. Okay, so that represents the width of the integral of the rectangles, but in terms of integrals, that also represents what we have to integrate with respect to. So the implication is this: every rectangle hits y equals x squared on the right, but I have to write that in terms of y. Y equals x squared is the same thing as x equals root y. That's an x. So every rectangle hits root y on the right. On the left, they hit y equals 1 over x. If you solve that for x, that's also 1 over y. So right minus left. Now my limits should tell me where is my lowest rectangle in terms of y. That would have been right here at y equals 1. And my highest horizontal rectangle would have been at y equals 9. And what is true is if you work out this single integral, it will come out to be the same as the sum of both of those because we're talking about the same area. And obviously, this would be easier, right, in terms of evaluating because you only have to do one integral. Now, a natural question to ask, and this will probably happen at some point, I've been telling you the best thing to do is to sketch the graph of the area that you're trying to find. But what if the equations you're asked to find the area between are too difficult to graph? So here's an example. Let's set up the integral or integrals for the area between f of x equals x to the fourth plus 16x and g of x is equal to x to the fifth, that's a 5, plus x to the fourth. Okay. Well, those are hard to sketch, but what we would want to know is where do they intersect, right? We want to have some intersection points. So one thing that would be good to find is the intersection points, which we can find by setting them equal to each other. And if I set both of these equations equal to each other, the x to the fourths cancel out. If I move the 16x over, do some factoring, I see that the graphs intersect each other at 0 and at plus or minus 2. So there's actually 3 x values where they intersect. So what I could then deduce is that I'm going to need 2 integrals. One integral is going to go from -2 to 0. That was my lowest point of intersection. And the other one's going to go from 0 to 2. Assuming we're using vertical rectangles, we decided that to find the height of one of my rectangles, it should be top minus bottom. But how do I know which function's on top if I can't graph it? Here's a trick. Pick a test number. My first integral goes from -2 to 0. So what if I picked a number in between, like -1, and I plugged in, I evaluated each function at -1. F of -1 was -15. G of -1 is 0. Since 0 is bigger than -15, that would be my top function in this interval. So the first integral is going to be g of x minus f of x. From 0 to 2, most of the time they switch, but not always. So the safe thing to do would also to be pick a test number between 0 and 2. I picked 1 again. This time f of 1 was 17 and g of 1 was +2. 17 is bigger, so that must have been my top function. So from 0 to 2, you would do f of x minus g of x. This was just a setup. To actually work it out, you'd still have quite a bit of work to do. So this gives you some idea on how to set up and work out integrals for the area between two curves, 2 or more curves.